Assalamu alaikum dear friends. Welcome to the lecture of the classical mechanics. In this lecture we will discuss the solution for the problem number 7.22 which is from the Marion books. The statement of the problem is like this: a particle of mass m move in a one dimension under the influence of force which is given by f of x of t is equal to k of x square exponential minus t over tau, where k and tau are positive constant. You compute the Lagrangian and Hamiltonian function. First we will find the Lagrangian and Hamiltonian, then compare the Hamiltonians and the total energies and discuss the conservation of energy for the system, whether the energy is conserved for the system or not. So the very first thing that we are given with that the potential energies we are given with the force. So if we are given with the force which is f of x of t is equal to k of x square exponential minus t over tau, so we can find the potential energy from this force if this force is conservative. So f of x is equal to minus partial u over partial x if this force is conservative. So this force will be can be written as negative derivatives of potential energy with respect to that variables. So f is equal to minus partial u over partial x. So if we want to find the potential energy, so we will just integrate this equation. That will be u will be equal to minus f dot dx. If we are given with the force, so we will just integrate this with respect to x. So it will give us u is equal to k of x exponential minus t over tau. It means we have to integrate this equation. Means we are given with the force, put this force in this equation and dx and integrate this with respect to x. So it will give us u is equal to k of x exponential minus t over tau. And the next step is writing the Lagrangian. So because our first task was the computing the Lagrangian, it means Lagrangian is equal to T minus U. So we have kinetic energy which is equal to m over 2 x dot square. If particle is moving in one dimension along x, so its kinetic energy will be equal to m over 2 x dot square, which is equal to m over 2 x dot square minus potential energy. So this is potential energy. We will plug just this u which is equal to k over x minus exponential minus t over tau. So we will plug this potential energies u in this expression. So it will become mx dot square over 2 minus k over x exponential minus t over tau. So this is Lagrangian. Now the next target is Hamiltonian. We have an expression which relate these parameters. Hamiltonian is equal to px x dot minus l. You know that px, this px, we can find this px which is equal to partial l over partial x dot. You know that we have Lagrangian, we can take a derivative with respect to x dot. It will give us px. Once we find the px, we will plug this into this expression and then we have already Lagrangian. So these two parameters will give us Hamiltonian. So h is equal to px multiplied by x dot minus l. So px is equal to partial l over partial x dot. First we will take the derivative of Lagrangian with respect to x dot. If we take this derivative of this Lagrangian with respect to x dot, so it will give px. Then plugging into this equation partial l over partial x dot, value of partial l over partial x dot, we can find the value of this partial l over partial x dot by taking the derivative of this Lagrangian with respect to x dot, and then plugging this Lagrangian in the place of this or here. So this will give h is equal to px square over 2m plus k over x exponential minus t over tau. This is a very simple step. Just we need to find the px, which is partial L over partial x dot, and then plug this Lagrangian into this expression, multiply with x dot, so it will give x mx dot square m square x dot square, so it will become px square and 2m plus some other term k over m k over x exponential minus t over k. So thus we have find the Hamiltonian. And our next task was the compare the Hamiltonian and the total energy. Now we will see the Hamiltonian is equal to the total energy T plus Q, because this is the kinetic energy and the second step is potential energy. So our Hamiltonian is equal to just total energy, because total energy is equal to kinetic energy plus potential energy. And the second step is we have to discuss whether this energy is conserved or not, which is because the potential does not depend upon velocity, but the total energy of the system is not conserved. Why this is not conserved? Because this total energy depends upon the time. It means as the time goes on, this exponential minus factor will decrease this term, and energy will change with respect to time. Energy will decrease with respect to time, and its energy will not remain constant. So its energy does not remain conserved for this system. I think these are the requirements in question statements. So I will stop at this point and we meet in the next lectures.